Howdy everyone, I'm Joshua Zimmerman and this is my final project for computer animation. My goal was to make a 3D Eulerian simulation that uses some sophisticated methods for representing the movements of gas in a static area. My inspiration for this project was seeing many cool implementations of smoke as well as fog on YouTube and other such platforms, and wanting to combine this with the use of time step-based simulations that we used in Assignment 5. I set out to make a system that could properly simulate gas with variable levels of detail based on the application you intended to use it for, and the result could be fully visualized in a rendering/animation software like Blender. At the core of the simulation is a grid made up of cells that each hold velocity, density, pressure, and temperature, like a real gas would. Initially, the grid is empty. However, through something called injection, we can add density into some cells into the grid slowly throughout the simulation to give an effect close to what you would expect from something like a campfire. These dense cells are now given some initial velocity, temperature, and then we can run a simulation step like we did in Assignment 5. A problem I ran into in development close to around setting up this point of the simulation was getting the injection equation balanced. If you add too much density, your simulation will turn into more of like an explosion and break immediately, making it hard to test other parts of your simulation that you're integrating as well. While adding too much temperature can also do the same thing. So the way that I solved this was throughout my development, I tried to keep things as close to real world units as possible in every step. And pick an expected density value in Blender to try to aim for an equilibrium through trial and error. Simulation step consists of applying buoyancy to make the gas rise based on its temperature and density at any given cell. Then we can apply vorticity confinement to add vortices or small-scale swirls that you would typically lose with smoothing. And then we can diffuse velocity, which is akin to internal friction, or viscosity, think honey versus water. And then we can project pressure to ensure that no gas accumulates and disappears, making the simulator incompressible. We follow this up by advecting velocity in the grid, carrying the velocity values through adjacent cells, mimicking real gas movement, and then projecting pressure again after introducing possible divergence. So you can imagine at these diffusion and advection steps where we're basically applying forces to neighbors based on whatever variables that we have, we can run into over smoothing or like laminar flow in the instance of fluids where things tend to be way smoother than they would be in real life. And that kind of relates back to the vorticity confinement and why it's important. We can then diffuse and advect temperature as well as density in a similar way, and then enforce boundary conditions on the grid to make sure no gas escapes. I used some of the more mathematical concept from this class, like constructing sparse matrices out of triplets to construct 7-point finite difference stencils that approximates the Laplacian matrix, a matrix used in diffusion equations as well as Poisson equations for pressure projection. This made my complex calculations manageable by Eigen and its sparse matrix/linear solver capabilities, which greatly simplified everything for me. Lastly, I use OpenVDB, a commonly used open source graphic system for storing and formatting volumetric data, specifically density of gas within cells of the grid. Using OpenVDB, I can export each simulation frame, then load each frame into Blender as a sequence similar to the frame sequencing that we used in Assignment 3. Thank you guys for watching my presentation on my final project. I hope this was interesting to you and you learned something.